If you work in infrastructure, you know the exact flavor of adrenaline that hits when a pager goes off at 2 a.m. Usually, it's a failed rehash of a storage archive or an overly aggressive high availability pair that triggered immediately, leaving you debugging hardware clusters before breakfast. But running production workloads on AWS Spot instances, hardware explicitly designed to be interrupted and taken away, has never triggered one of those late-night emergencies for me. Not once. Spot instances are simply spare compute capacity. Cloud providers like AWS sell this unused hardware at a massive discount, with one strict condition: they can reclaim it at any time when they need it back for full-paying customers. Late-night outages are not an inherent rule of the cloud. They are a symptom of architecture unprepared for failure. When an engineering team gets burned by a reclamation, the standard response is to label Spot instances as unreliable. Look at the incident report, and you will almost always find the same architectural flaw. The workload was restricted to a single instance type, running in a single availability zone. When standard on-demand capacity tightens in that specific zone, AWS reclaims the Spot hardware. Because the architecture dictates only one acceptable replacement type, and that type is suddenly scarce, the workload has nowhere to migrate. The operations team subsequently abandons the discounted hardware, moves the exact same architecture to standard on-demand instances, and blames the pricing model for the downtime. Several days later, a routine, silent hardware failure hits the newly migrated on-demand server. The resulting system crash is identical to the Spot reclamation event. The auto-scaling group, the service responsible for automatically adjusting the number of compute instances, cannot register the failure because the underlying EC2 server is failing health checks it can no longer conduct. EC2, or Elastic Compute Cloud, provides the virtualized server hardware where these workloads run. The Spot pricing model didn't cause the initial downtime. A fragile, single point of failure architecture simply exposed itself twice. Amazon CTO Werner Vogels summarized cloud computing with a simple axiom: everything fails all the time. Standard hardware failure on an on-demand instance is random, silent, and immediate. The server is there, and then it isn't, triggering a reactive chain of dominoes across the entire system. Compare that to a Spot reclamation. AWS delivers an interruption notice via EventBridge, creating a deterministic countdown. You get exactly 2 minutes of operational runway. That is enough time to cleanly hand off tasks to a stable node before the hardware is taken away. Utilizing this window requires strict engineering discipline. The application must use idempotent operations, meaning a task can be retried multiple times without corrupting the final result, and nothing can be stored locally on RAM or disk. RAM is the short-term data storage a processor uses to run applications. If your system is robust enough to survive random, silent hardware deaths, it handles a failure that politely announces itself in advance for free. To understand how to survive these planned interruptions, we need to look at capacity pools. A pool is a collection of compute instances grouped by 3 specific variables: the hardware type, its size, and its geographic location. Spreading a workload across multiple pools does not lower the interruption rate of any individual pool. If AWS needs a specific instance type back, they will take it. Multi-pool diversification shrinks the blast radius. In a single pool, a reclamation causes an immediate blackout. A resilient strategy uses 5 distinct pools. When a reclamation hits, the impact is a fractional drop. The automated scheduler perfectly replaces the lost nodes from surviving pools. While varying instance sizes is helpful, true resilience requires diversification across different availability zones and entirely different processor families. Surviving on Spot is not about outsmarting interruptions. It is about mathematically structuring the environment so that a localized outage becomes nothing more than a routine background capacity adjustment. Achieving this diversification requires abandoning the standard engineering practice of hard-coding specific instance brands, like an M5.larch, into configuration files. The superior alternative is attribute-based instance selection. Instead of requesting a rigid hardware name, you define a compute shape. This means requesting a flexible range of vCPU and memory that meets the application's requirements. vCPU, or Virtual Central Processing Unit, represents a share of a physical processor's power allocated to a virtual machine. Tools like Carpenter, an open-source Kubernetes cluster autoscaler, natively evaluate these compute shapes. They asynchronously provision nodes from dozens of matching types, entirely removing the need to manage static node groups. When configuring these tools, avoid the lowest price allocation strategy. This setting forces workloads to violently shift between the absolute cheapest available pools, resulting in highly frequent interruption rates. The price capacity optimized strategy is far more effective. It balances marginal cost increases against massive gains in overall stability. By moving from rigid infrastructure requests to flexible compute shapes, teams broaden their survival options while letting automated schedulers handle the underlying price optimization. There is one non-negotiable rule of ephemeral compute. You never run databases or stateful user sessions directly on Spot instances. State acts as memory. Losing a stateful node means the permanent, unrecoverable destruction of active customer data or hours of ongoing work. Nothing can be stored locally for longer than that 2-minute warning window. True fault tolerance requires externalizing all outputs to permanent storage solutions like S3 or managed databases. This ensures any compute node can die instantly without taking the data with it. Architecting a platform to support both standard x86 processors and ARM-based chips like AWS Graviton generates a compounding financial multiplier. x86 and ARM refer to different instruction set architectures that dictate how processor hardware executes software commands. Graviton processors already run 10 to 15% cheaper than their Intel equivalents. When you apply the up to 90% Spot discount on top of that base reduction, the math begins to compound aggressively. The platform remains tolerant of capacity fluctuations, launching instances wherever hardware is available or regional prices drop across the globe. This contract-free model allows an engineering team to spin up 600,000 vCPUs for a massive computational workload and instantly terminate them a week later. Operating at this scale requires zero multi-year financial commitments. The only contract is the ephemeral nature of the infrastructure itself. The deep discounts provided by Spot are not a gamble or a hack. They are a direct financial dividend paid exclusively to teams who have successfully mastered the first principles of stateless, resilient architecture.